Welcome back, guys. This is going to be your 7.1 instructional video. And in this video, we're going to introduce systems of equations. Okay, we've just come off of chapter 6, where we learned all about linear equations. We learned about slope. We learned about different forms of linear equations, writing equations of trend lines, graphing linear equations, all that good stuff. And what we're going to do is we're going to take that chapter 6 knowledge and use it to work with systems of linear equations. Systems of linear equations meaning multiple linear equations at the same time. Okay, so what we're going to do is we're going to work with those. And in 7.1, 7.2, and 7.3, we're going to learn how to solve systems of linear equations. We're going to learn how to solve systems of linear equations. And there are 3 different methods. 7.1 is going to be graphing. So if you have some graph paper laying around, I'd use that. 7.2 and 7.3 will be some other methods. But again, chapter 7, systems of linear equations. We're going to solve them. What's a system of linear equations? It's when we have 2 or more equations of lines together. So let's dive in. Okay, so what we're going to do is we are going to graph the following equations. Okay, what we see here is a system of linear equations. And again, what a system of linear equations is 2 or more equations of lines together. Okay? And what we want to do is we want to find a solution. And if we think back, what is a solution to an equation? Well, it's any number that makes the equation true. Now, in this case, when we're looking at these linear equations, we have 2 variables, the y and the x. So a solution to y equals 2x minus 3 will be a coordinate pair. It will be a value for x and a value for y that make that equation true. Okay? We've seen some of this before in earlier chapters. What we haven't seen before is a system of equations. So what we're going to do is now we have multiple equations, each equation with 2 variables, both lines. And what we're going to do is we are going to find an ordered pair or set of ordered pairs that make this system of linear equations true. Okay, essentially we're looking for the value or values that when plugged in will not only make one of the equations true, will make both true. In 7.1, we're going to do that by graphing. Okay, so while you may not be familiar with systems of linear equations, I know you know how to graph these. So how are we going to graph them? Well, I would recommend you pause the video and try it on your own. Okay, so hopefully you've taken a shot, you've graphed both of these on the same coordinate plane. What we're going to do is we are going to graph these, and again, because it's a system, 2 or more equations of lines together, we're going to graph them on the same coordinate plane. And what we're going to do is we're going to look for their intersection. Okay, we're going to kind of see what pops out to us. So this first equation, hopefully remember from chapter 6, is in slope-intercept form. So what I'm going to do is I'm going to identify the slope and the y-intercept, since it's in slope-intercept form. The y-intercept being minus 3. The slope is 2, so I will go up 2 over 1. Up 2 over 1. And I could also go down 2 left 1 if I wanted. And these dots, when I connect them all together, will create the line resembling y equals 2x minus 3. But again, this is a system of linear equations, so I need to now graph the other one. And that has a y-intercept of negative 1 and a slope of 1. So I'll go up 1 over 1, up 1 over 1, up 1 over 1. And now I will connect these with a line. And what do we notice? Well, we notice that we have 2 lines, which we expect because we have 2 linear equations. But what we notice is they intersect. Specifically, they intersect at the point 2, 1. What this means is the intersection will be the solution to the system of linear equations. Okay? That's the whole idea with 7.1. If I were to sum it up in one sentence, it's we find the solution to a system of linear equations by graphing the equations and seeing where they intersect. We graph each linear equation. We see they intersect at 2, 1. How do I know that this is the solution, or how could I check my work? Well, think about what a solution means. Again, a solution to a linear equation or a system of linear equations means when you plug it in, we're going to get a true mathematical statement. Okay, what we're looking for is the point that makes both linear equations true. So what I'm going to do is I'm going to plug this coordinate point in. So if I look at y equals 2x minus 3, I'm going to plug in 1 for my y value, since it's the y coordinate of the solution, and 2 for my x value. When I do this, I get 1 equals 4 minus 3, which is 1. So I get 1 equals 1, which is a true math statement. A true math statement. Now, this hopefully looks familiar. We've done this before, checking our work with equations. But what we've never had is a system of equations or multiple equations that we had to satisfy. So if the intersection, this point 2, 1, is indeed the solution to the system of linear equations, it should not only make the first equation true, but it also should make the other equation true. So again, plug in 2 for x, 1 for y, and we get a true math statement. If you didn't get a true math statement, that means that that solution that you came up with is not, in fact, a solution to the system of linear equations. You probably made a mistake somewhere. So always check your work. Take your potential solution and plug it into your equations. If when you do it, both produce true math statements, they are balanced equations, then you indeed have found the solution. Okay? So what are the definitions? What's our process here? Well, when you graph two equations in a system of linear equations, where they intersect is the solution. This hopefully gives you in definition form, again, I'd write this down, what we're really trying to do. We're trying to find the intersection via graphing of the two linear equations. Why? Because that intersection will be the solution. Okay, it will be the solution. What do I mean by solution? Again, those are values or coordinate points that make both equations true, right? It's the x and the y values that when plugged into the equation make the equation true. Okay? So, and again, this note here, this is just one way to find the solution to this system. Graphing and finding that intersection, which will in turn be our solution. And again, always check your work. But this is only one method. We're going to learn other methods in 7.2 and 7.3 that don't involve graphing. But 7.1, we're going to solve systems of equations by graphing. So let's try another table. Again, I would encourage you to try this on your own. We want to find the solution to the system of linear equations. So pause the video and give it a shot. Then I'll solve it. Well, again, what I notice here when I go to solve this is both equations are in slope-intercept form. Slope-intercept form. So when I look at the first one, if it's in slope-intercept form, what I notice is that we have a slope and a y-intercept. So I'm going to plot my y-intercept. And then according to my slope, I need to go down 1 over 2. Down 1 over 2. Down 1 over 2. If graphing in slope-intercept form is very difficult for you, you need to email me or come see me sometime. Again, that's more of a Chapter 6 skill, and we need to obviously have that skill in order to do Chapter 7. So please make sure if you're struggling with graphing in slope-intercept, you come see me. Now we want to graph the green line, y equals negative 3x minus 3. So I'm going to put my y-intercept at negative 3, and then I'm going to go down 3. Over 1, down 3, over 1. I also could go up 3, left 1, up 3, left 1, up 3. I want 2, up 3, left 1. And we have our 2, or I didn't go up 3, I'm sorry. 1, 2, 3, 4. Okay. Now that I have my dots, I can connect them with my line. And I can very clearly see beginning of that line's not very straight. What I can see is that these lines do intersect, and where they intersect is at -2, +3. -2, +3. So again, I will deem that the potential solution to the system of linear equations, the coordinate pair that makes both linear equations true. That is my solution. So how can I check that though? We'll plug in your values. -2 is the x coordinate, so let's plug that in for x and see if we get our y value, which is 3. Well, -1/2 times -2 is 1, plus 2 is in fact 3. So my solution satisfies my first equation, but I got to check my second one as well. -3 times -2 minus 3, again, does that equal 3? Well, -2 times -3 is 6, minus 3, we do get a true math statement. So what we would say is the solution to the system of linear equations is -2, 3. And we can see that in the intersection in the graph. Okay? If you know Caroline Fay, she wanted to be the example in this problem, so she is going to be our example. Apparently, Caroline decided to buy bamboo plants. After purchasing the plants, she is now trying to figure out which fertilizer will help the plants grow the best. Plant A is 6 centimeters tall and growing at a rate of 4 centimeters per day. Plant B is 10 centimeters tall and growing at a rate of 2 centimeters per day. When will the bamboo plants have the same height, and what is that height? Again, I'd recommend trying to solve it on your own and check your work with mine. So Caroline's buying these bamboo plants, and she's now trying to figure out which fertilizer is going to help them grow the best. So she tests the one fertilizer on the one plant, tests the other fertilizer on the other plant. Okay? So what we're going to see here with Caroline is we're trying to figure out the height of the plants, right? And we want to know when they're going to have the same height and what is that height. So first things first, let's come up with equations for each plant. Let's come up with equations for each plant. Because before we can use our knowledge of systems of linear equations, specifically graphing them to figure out where they intersect, what we have to do is we have to come up with the equations first. So what do we know? Well, we know plant A is 6 centimeters tall and growing at a rate of 4 centimeters per day. It's 4 centimeters per day. So we can write an equation for this. We recognize that it's 6 centimeters tall at the beginning, plus it's growing 4 centimeters every single day. Now, we don't know how many days we're going to watch it grow, so we'll throw in a variable. Maybe we throw in the variable x for it. So x is the number of days that have gone by. And what do I achieve by taking 6 and adding 4x to it, x being the number of days multiplied by 4? Well, what I'm going to get is I'm going to get the total height of the plant, which we could call y. Y is the height. We'll get the total height of the plant depending on how many days. Okay, so this is our linear equation. If I take 6 and I add 4 times the number of days to it, I'm going to get the current height of the plant, given the idea that the plant is 6 centimeters tall and growing at a rate of growing at a rate of 4 centimeters per day. What about plant B? Well, for plant B, it starts out at 10 centimeters tall, but it's only growing 2 centimeters every single day. We already said days was going to be x. And again, by taking the initial height and adding how much it grows every day times the number of days, I get the total height, which we already deemed to be y. So I'm using my knowledge and the information that the problem has given me. Now I have set up a system of linear equations, right? I have an equation resembling the height of plant A and how it changes over time, as well as an equation for the height of plant B as it changes over time. But that doesn't solve my problem. While it's great that I came up with the equations, I'm trying to figure out when the bamboo plants will have the same height and what that height is. So how am I going to figure that out? Well, what I'm looking for is when will they have the same height? I want to know what day they have the same height. How do I find day? Well, day is an x value. So I want to find the x value that, or I want to find the x value that when the x value is the same, the height is also the same. In other words, I need to find where these two linear equations are going to intersect. What's the solution to them? What is the x value such that when it's plugged into both equations gives me the same y? Again, why do I want to know that? Because x is my number of days and y is my height. And I want to know when the bamboo plants will have the same height and what that height is. Well, our only method for solving linear equations to this point is graphing. So let's do it. Y is my height, and I think it'd probably be best if I go up by 2's. My grid lines will go up by 2's. I'm going to mark every other grid line, though. So it might look visually like I'm going up by 4's, but really I'm going up by 2's. And then my x-axis, days, we can just go by 1's. Again, my grid lines will go by 1's, but I'm going to only label every other grid line. And now I can graph these. Again, these are in slope-intercept form. So I will plot a dot at 6, and I will go up 4 over 1, up 4 over 1, up 4 over 1. Draw a little line. And again, notice I'm having it shoot upward, but I'm stopping at the y-axis, and I'm not going any further left, or I'm not going below the x-axis. Why? Again, we have context here. We need to remember that x is our number of days and y is our height. The plant cannot go back in time, and the plant can't have a negative height. So we're not going to have our arrow, unlike our problems that don't have context, continue down. Graph for plant B, we're going to start at 10. We're going to go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and connect with a line. And what I find is that they intersect at the point 2, 14. My graphs intersect at 2, 14. And from our new knowledge of linear equations, we know that this is the solution to the system of linear equations. In other words, if I took the point 2, 14, and I plugged in 2 in for x and 14 for y, I'm going to get a true math statement for both plant A's equation and plant B. This is the solution, right? And we can see this visually here, right? Initially, plant B is a little bit taller, but isn't growing as quickly, whereas plant A was a little bit shorter, but with that fertilizer, it's increasing in height, and eventually it overtakes the height of plant B, but there is a moment in time when they have the same height, and that intersection, by finding the solution to the system of linear equations, I know on what day they have the same height and what that height is. Okay, in order to figure that out, again, we have 214. Remember what our labels are. If x is our number of days and our solution is at 214, then the bamboo plants will have the same height after 2 days. And that height will be 14 centimeters. Okay, again, that's why it's really important to label x as our number of days and y as our height. I'm okay working with x and y here. We just want to have good labeling. So this is going to end the instruction for the first part of 7.1. A second part will be coming shortly. Again, hopefully what you're walking away with is, while we learned about linear equations in Chapter 6, now we're going to be working with multiple linear equations, known as a system of linear equations. And the first way that we have learned to find a solution to a system of linear equations is figuring out where their graphs intersect. So we use our graphing knowledge from Chapter 6 to find the intersection point for a system of linear equations, which in turn is the solution, the values that make both linear equations true. Thanks for watching, and again, that second part will be coming soon.